During this segment, we'll discuss what we mean by a function. But before we talk about functions, let's talk about ordered pairs and equations in two variables. We have been discussing the relationship between, we've been normally using x and y, so the relationship between the variables x and y by talking about ordered pairs of numbers and also equations in two variables. So let's talk about what we mean then by a relation. Let's give a definition. A set of ordered pairs is called a relation. The x-coordinates in the set of ordered pairs is called the domain of the relation, and the y-coordinates, that set of y-coordinates in the relation, is called the range. So I've defined relation, I've defined domain, and I've defined range. Now my definition for relation is a set of ordered pairs. Can you see, because an equation in two variables does define a set of ordered pairs, then we can also talk about the fact that an equation in two variables can also define a relation. We've got a vague idea about the definition of a relation. Let's now look at a set of ordered pairs. This is, by definition then, a relation. A set of ordered pairs is a relation. Let's take this set of ordered pairs, let's find the domain and range of this relation. So what is the domain of this relation? It is the set of all x-coordinates in the ordered pairs. So what is the set of all x-coordinates? It's the set containing 0, 1, and 5. 0, 1, and 5. There is the domain of this relation. What is the range? The range is the set of all y values or y coordinates. So I have -2, and then -2 again. There's no sense writing it down twice, and then -2 again. So my range consists of one value, and that value is -2. Now that we've talked a little bit about relations, there are special relations called functions. Let's now look at a definition of a function. A function is a set of ordered pairs that assigns to each x value exactly one y value. We will continuously be talking about functions, but remember, a function is a set of ordered pairs, so it is a relation that assigns to each x value one y value. So here I have a relation. I'd like to know, is this relation also a function? To check, let's check each x value and see if one ordered pair or one y value, is assigned to that x value. Here's the x value 1. This x value goes with or is paired with only one y value, 1 also. So I'm okay there. This x value 2 is assigned or paired with one y value, 2. This x value -3 is paired with a single y value, -3, and this x value 0 is paired with just one y value, 0. So this is, yes, a function. And we'll learn more and more about functions, but right now we know this is an example of a function. Let's look at another set of ordered pairs and see whether the relation is also a function. -1, 0, -1, 6, and -1, 8. All right, I have a set of ordered pairs, so this is a relation. By the way, what's the domain of this relation? It is the set consisting of, I just have one x value, -1. What's the range of the relation? It's the set consisting of 0, 6, and 8. But I'd like to know if this relation is also a function. To find out, let's look at the ordered pairs. This x value of -1 is paired with 0. But this x value of -1, it's also paired with 6, and it's also paired with 8. Remember, a set of ordered pairs is a function if the x value is paired with just one y value. Because that does not happen here, no, this is not a function. Let's look at a few other examples and see whether these representations of ordered pairs are functions. Here I've represented a set of ordered pairs by graphing the ordered pairs. I'd still like to know, is this relation also a function? Well, let's look graphically. It is a function if each x value is assigned or paired with a single y value. So here I have, say, the x value of -1 paired with the y value of -1, and we can see -1 for x is paired with no other y values. Now notice the x value 1. I have the x value 1 paired with the y value 1, but I also have the x value 1 paired with the y value -1. Because you can see along this line that the x value 1 is paired with two different y values. So I don't even need to look at this other point or its corresponding ordered pair. I know right now that I do not have a function. This is no, not a function. Let's look at one more example. Let's decide if this represents a function. Now we said a set of ordered pairs is a relation. Don't forget that a line is made up of points, and points are associated with ordered pairs of numbers, and ordered pairs are associated with relations. So is the relation defined by all of these ordered pairs also a function? Well, let's just go through a few examples. Just take a few points. For example, this point, it has an x value of -2, and whatever the y value is, it looks like maybe -3, but who knows? Can you see it has only one y value associated with it? Or we'd have another point somewhere along the way. This x value, say, of 3, it corresponds to one y value only. If not, I'd have another point along this vertical line. So since every single x value is assigned or paired with one y value, then yes, this does describe a function. Yes, this is a function. Now there is a simple way, if you have a graph, of deciding whether the graph represents the graph of a function. This way is called a vertical line test. Let's look a moment. Notice that if a vertical line touches this graph at most once, then we do have the graph of a function. So here's the vertical line test. If a vertical line can be drawn so that it intersects a graph more than once, the graph is not the graph of a function. Let's use the vertical line test to see if this represents a function. Can a vertical line be drawn so that it cuts or intersects this graph more than once? The answer is no. There is no vertical line that can be drawn that will intersect this graph more than once. So yes, this is the graph of a function. Study this graph a moment and decide if it is the graph of a function. Can you draw a vertical line that intersects this graph more than once? The answer is no, so yes, this is a function. Study this graph a moment and tell us whether you think this is the graph of a function. Can you draw a vertical line that cuts or intersects this graph more than once? The answer is yes. There are, in fact, many vertical lines that can be drawn that intersect this graph more than once. Just so you'll understand why the vertical line test works, let's suppose this point is 4, 4, and let's suppose this point is 4, -4. Can you see why the vertical line test works? Notice if I can draw a vertical line so that it cuts the graph more than once, such as I can do here amongst many other places, what does that mean in terms of the definition of a function? It means that we have an x value that is assigned to more than one y value. Remember, a set of ordered pairs is a function if every x value is assigned or paired with exactly one y value. So this negates the definition of a function because it does, and of course the same thing with the vertical line test, no, we do not have a function. Here I have the graph of a vertical line. Is this graph the graph of a function? Can you draw a vertical line that intersects this graph more than once? The answer is yes. If I drew this vertical line, it intersects the graph in an infinite number of places, so because of that, this vertical line does not represent a function. By the way, can you see that no vertical line actually represents the graph of a function? But to answer the question, no, this is not a function. And this is by the vertical line test. Let's suppose we have an equation, y equals x squared plus 2. This is a relation. It defines a relation between x values and y values. Let's suppose I tell you that if you graph this relation, the graph passes the vertical line test, so you do indeed have a function. If we'd like, then, we can use function notation to name this function. And we normally use letters such as f, g, and h, but we will use function notation now to name this function since we do indeed have one. Instead of y, then, we'll write f of x, function of x. Now, the most important part here is to remember that this is not multiplication. This is not f times x. It is a special function notation, and we read this as f of x is equal to x squared plus 2. To become used to this function notation, let's practice evaluating at certain values. In other words, given this function notation, let's suppose we want to find f of -2. Now, how might you think we'd find f of -2? And what does f of -2 mean? Notice x is replaced with -2. So throughout, instead of x, I replace x with that replacement value, -2. I am finding the value of the function at -2. So let's evaluate on the right side. -2 squared, that's -2 times -2, which is +4, and then 4 plus 2 is 6. So it is true that f of -2 is equal to 6. So looking at this, what is the x value and what is the y value? How can I write this in a corresponding ordered pair? Well, remember, this -2 replaced x, so as a corresponding ordered pair, x is -2, and f of -2, which is 6, that's the y value. Very important for you to be able to write from function notation to ordered pair notation. but let's practice this again. Let's find, given this function, let's find f of 0. Now, how do we find f of 0? Notice x has been replaced with 0, so we do that throughout. Instead of x, I write 0 and then squared plus 2. And now we evaluate on the right side. This is 0 squared is 0, and then 0 plus 2 is 2. So we have that f of 0 is 2. Now let's go ahead and practice also writing this as a corresponding ordered pair. If f of 0 is 2, what is the corresponding ordered pair? When x is 0, f of 0 or y is 2. So there's our corresponding ordered pair. And then let's try this one more time. Given this function, let's find, say, f of 3. All right, so how do we find f of 3? We replace x with 3, so that's 3 squared plus 2. 3 squared is 9. That's 3 times 3, which is 9. And then 9 plus 2 is 11. So what do we have? We have f of 3 is 11. That's the value of the function when x is 3. Let's go ahead too and practice writing this as a corresponding ordered pair. How do we do so? When x is 3, f of 3 or y is 11. So here is a corresponding ordered pair. But there's a little bit about function notation. Let's now practice writing the domain and range of functions from graphs. By the way, some of these will be functions, some may be relations, so let's also practice finding out whether we have a function or not. So by the vertical line test, is this a function or not? By the vertical line test, this is the graph of a function. I'd like to find the domain. Remember, domain has to do with x values. So what x values do we have included on this graph? To find out, we simply need to know how far left this graph goes and how far right, because that has to do with the x-axis or x values. So how far left does this graph eventually go? How far right? Because of this arrow, this graph goes toward negative infinity. And how far in the positive sense does this graph go? Because of this arrow, this graph goes toward positive infinity. So what is the domain? And we'll write it in interval notation. The domain is from negative infinity to positive infinity. Again, for domain, you look how far left, how far right. Now let's talk about the range of this function. For range, since that has to do with y values, we look at how far down and how far up. Now, how far down does this go in the y sense? Can you see that the smallest y value is -4, and then how far up toward the infinity area or toward infinity? Since we have these arrows, this graph does approach infinity in the y sense. So how far down? The smallest y value is -4, and I put a bracket because this does actually reach -4 in the y sense. And then how far up? Positive infinity. There is the domain and the range of this function. Here we have another graph. I'd like to decide if this is the graph of a function. Whether it is or is not, we still want to find the domain and range of this function or relation. So do we have the graph of a function? Remember the vertical line test? If you can draw a vertical line that cuts this graph or intersects this graph in more than one place, you do not have the graph of a function. You can't do that, so this is the graph of a function. In fact, all horizontal lines represent functions. But anyway, this is a function. Let's find the domain and the range of this function. Now, how do we find the domain when given the graph? We simply see how far left and how far right, this graph runs. How far left, how far right, because that tells us what x values, and we have x values meaning domain. So, how far left does this graph go? Well, it is going toward negative infinity. How far right? It's going toward positive infinity. So, as far as x values go, in interval notation, the domain is from negative infinity to infinity. And now, what is the range of this function? For range, because we are talking about y values, you see how far down and how far up. Well, how far down does this graph go and how far up does this graph go? In fact, if you look at a few ordered pairs, there is only one value or element in the range, and it is what? It is the number 2. So the range consists of one number, and it is the number 2. There is the domain, and there is the range of this function. Do we have the graph of a function? This is certainly a relation, but is it also a function? The answer is no. You can draw a vertical line that intersects this graph more than once. So this is not a function, but regardless, we still want to find the domain and range of this relation. So let's talk about domain. To talk about domain, we talk about how far left and how far right as far as this graph goes. So, how far left does the graph go? How far right does the graph go? Well, by simply looking at a few ordered pairs that are of this graph, you can see that there's only one x value in this entire graph, and that x value is the x value 3. So the domain contains one number. It is the number 3. There is the domain of this relation. What about the range? What do we think about for range? For range, we think about how far down does the graph go and how far up, because range has to do with y values. So how far down? Well, this is approaching negative infinity. How far up? This is approaching infinity. So what is the range of this relation? It's from negative infinity to infinity. There's the domain and range of this relation. At this time, practice using function notation and practice determining whether you have a function by looking at the graph and using the vertical line test. Also practice finding domain and range of a function or a relation.